All right. Well, hello, Discrete Math. I've got a few more videos for you guys. Finally getting around to getting these Chapter 2 videos made. We're still going to follow the schedule that I originally sent out after spring break. So we will have our Chapter 2 quiz on Wednesday this week. I understand that with the videos not getting posted until Monday today, that you might not be ready by Wednesday. So I'm going to also offer you Friday. So both Wednesday and Friday from 8 a.m. to 4 p.m. I will have the video, or I'll have the quiz for Chapter 2 up on Unify. That way, if you'd like to take it, you can. And then we'll be kind of starting Chapter 3, I guess, on Thursday, Friday this week. That'll mean Chapter 3 quiz will be probably next Wednesday. And then really we kind of wrap things up at that point. We take quiz, um, we study for the final, or the midterm number 2, and then the final exam. And then that'll be it, guys. We'll be done. And again, if depending on how you do with the midterm number 2 and final, I can always use those to replace your midterm number 1 grade. So if that is something you're working towards, just know that that is coming up very quickly on us. So that being said, let's jump into 2.1, which is our introduction to what's called weighted voting. So weighted voting. In a democracy, we take many things for granted, not the least of which is the idea that we think that we're all equal. But when it comes to voting rights, democratic ideal of equality translates into the principle of what's called one person, one vote. But is that always fair? Should one person, one vote apply when the voters are institutions or governments rather than individuals? So what we're talking about here is the exact opposite of the principle of one voter, one vote. A principle that's usually described as voter X votes, and what's called weighted voting. So weighted voting is actually not all that uncommon. We actually see it all the time in shareholder votes with corporations, business partnerships, legislatures, the United Nations, and probably the most infamous is the way we elect the President of the United States, also known as the Electoral College. So the Electoral College consists of 51 voters, if you think about it. Those are the 50 states, plus you've got the District of Columbia. And each of those is given a weight determined by its size of congressional delegation, which is that you take the number of representatives plus the number of senators. Now, each state gets 2 senators, and they all have at least 1 representative. So the kind of largest end of that is California, which has 55 electoral votes, and kind of the smallest then are the smaller states like Wyoming, Montana, North Dakota, DC, which only have the 3. Uh, and obviously all the other ones kind of fall in between. Now, obviously, this has been brought into a lot more attention based on 2000 and 2004 presidential elections, which were very, very close. Brought the Electoral College kind of into the spotlight, how it gets used, why we use it, what its role is with electing the president, and especially the pivotal role that can happen with just a single state. So going back to Florida in 2000 and Ohio in 2004, which actually had the final outcome of a presidential election come down to how their state voted. So in this chapter, what we're going to do is we're going to look at what the mathematics are behind this idea of weighted voting, with a particular focus on the question of what's called power. So first off, our formal definition, when we talk about weighted voting system, we are describing any formal voting arrangement in which the voters are not necessarily equal in terms of the number of votes that they control. We will only consider voting on yes and no matters, which are going to be known as motions. So there's no yes, no, maybe. Note that any vote between 2 choices, if we call them A and B, can be rephrased as yes and no. So yes would be a vote for A, and no would be a vote for B. And then that implies that every weighted voting system is going to be characterized by the following 3 characteristics. Number 1 is the players. So the players are how we refer to the voters in a weighted voting system. A weighted voting system players may not be individuals, though. They might be corporations, governments, states, municipalities, countries, so on. We're going to use capital N to denote the number of players in a weighted voting system. Excuse me. And typically, unless there's a good reason not to, we're going to call the players P1, P2, all the way up to Pn for however many we have. Element number 2 is what's called the weights. So the hallmark of our weighted voting system is that each player is going to control a certain number of votes, which means that they're not necessarily all going to be equal. Those are going to be called the weight of the player. we're going to assume that all the weights are positive integers, and we're going to use W1, W2 all the way up to Wn to denote the weights of P1 up to Pn respectively. We're going to use capital V is equal to W1 plus W2 plus all the way up to Wn to denote the total number of votes that are present in the system. And if this doesn't make sense right now, I get it. We're going to look at some examples in just a little bit that'll hopefully make things a little bit more clear. So the last thing is what's called the quota. So in addition to your players' weights, every weighted system has a quota. The quota is the minimum number of votes that's required to pass a motion. The most common quota is a simple majority, but the quota can really be pretty much anything. It could be a majority, it could be 2/3, it could be 3/4, it could be a whole lot of different things. To give you a concrete example of this, for the U.S. Senate, it takes a simple majority to pass an ordinary law. So that would be your quota to pass a law. But it takes 60 votes to stop a filibuster. So that's your quota for a filibuster. And it takes a minimum of 2/3 of the votes to override a presidential veto. So there's your quota for the override. And so then in other systems, it just depends. They can be 3/4, 4/5. It could be all the way up to 100%, where they would need a unanimous decision to meet the quota. So the standard notion that we're going to use is going to be to use square brackets. So those will look something kind of like this. You'll have your square brackets, and then we'll say what our quota is first, followed by the weights of each of our players. So that'll look something kind of like this. And again, we're going to list the weights in numerical order, starting with the highest and then going down from there. So here that is once again, our generic weighted voting system within players. You've got your Q followed by a colon, and then W1 listed all the way to Wn, with W1 being the largest, W2 being the next largest, all the way down to Wn being the smallest. Okay, let's get you a concrete example so that hopefully we can make a little more sense of this. Suppose that we've got 4 partners who are deciding to start a new business venture. So to raise the $200,000 that they need, they issue 20 shares that are worth $10,000 each. So let's suppose that P1, the first player, buys 8 shares, P2 buys 7, P3 buys 3 shares, P4 buys 2 shares, with the usual agreement that 1 share equals 1 vote in our partnership. And let's suppose that the quota is set at 2/3 of the total number of votes. All right, so what that means for our quota. There were a total of 20 votes possible, so 2/3 of 20 would be 13 1/3. Since we can't have 1/3 of a vote, we'll have to go up by 1, so that would mean our quota is at 14. So using the notation that we were just talking about, we would list our partnership as 14 as our quota, colon 8732. Okay, so let's talk about something kind of interesting. Let's talk about the power behind what's called anarchy. So imagine the same partnership that we discussed in the previous example, with the difference being we're going to change our quota from 14 down to 10. We might be tempted to think of the partnership as the weighted voting system of 10, 8, 7, 3, 2, but there's a problem. The quota is too small, because now it's possible for both the yeses and noes to have enough votes to carry a particular motion. Because if you think about it, if you take your first and last two, well, you've got 8 plus 2 is, let's say, 10 for the yeses. But then you also have 7 plus 3 is 10 for the noes, which means that they've both met the quota of 10 needed to make the change, but that's not possible. It's a contradiction. So that results in a stalemate, since both the yeses and nos have enough votes to meet the quota. In general, when the quota requirement is less than a simple majority, so in this case less than 11, we have the potential for both sides of an issue to win, which is what we just saw. This is the kind of mathematical version of what we would think of as anarchy. Okay, so that was anarchy. Let's now talk about gridlock. So let's again think about the partnership that we first introduced, but now let's say the quota has increased to 21. So if you were to write that out, you'd have 21, and then we had 8, 7, 3, and 2. So if you think about it, we now need 21 votes in order to pass whatever venture capital we decide to do. But if you add those up, 8 plus 7 plus 3 plus 2, if you remember, that adds up to be 20, which means that you're never going to get to 21, even with all the votes that are in this system. It doesn't make much sense. And so no motion is ever going to pass. This is the mathematical version of what's called gridlock. Okay, so given that we expect our voting system to operate without anarchy and without gridlock, we're now going to assume that the quota is always going to be somewhere between a simple majority and unanimity. What that means for us in that previous example, remember there were 20 votes total. Oops, went too far. Let me go back here. Slowly getting there. All right, let me do this. There we go. Okay, believe this is where we're at. Cool. So if you recall in that example, we had a total of 20 votes that we were looking at. Wow, that was really bad. 20 votes that we were looking at. So it has to be somewhere between a simple majority and unanimity. So unanimity being the 20 and simple majority being 11. That tells us that our quota is going to have to be somewhere between 20 and 11. So those two restrictions define our range of possible values for our quota. So here that is, again, is that quota has to be between your value for the number of votes and half of that value for a simple majority. Okay, so let's again go back to that partnership that we introduced in example 2.1 for one last time. So this time, let's set the quota at Q is 19, which is acceptable because remember we said as long as the quota was greater than 10 and less than or equal to 20, then we're okay. So 19 is less than or equal to 20, so we're good. So here we can describe the partnership as our weighted voting system 19-8-7-3-2. What's interesting about this is that the only way a motion can pass is by the unanimous support of all the players. Even though it doesn't add up to be 20, the only way you can get 19 is for all of them to agree. Because notice that if you add up P1, P2, and P3, so 8 plus 7 plus 3, you get 18. They still need one more vote, but P4 has 2 votes, so you still need P4's votes to pass the motion. So really, in a practical sense, that means that it's really no different from each partner having one vote, and they would take a unanimous agreement of the 4 parties to pass a motion. In other words, it would really be kind of the same in a way as saying 4 is your quota and then 1 vote for each of the partners, because you'd have to have all 4 to agree in order to vote. All right, so the kind of surprising conclusion of what we were just talking about is that we're just describing a one person, one vote situation in disguise. Seems like a contradiction, only if we think of a one person, one vote as implying that all players have an equal number of votes, rather than an equal say in the outcome of the election. So that's where it's important to decide to kind of understand the difference between the number of votes and the power, if you will, being different for this. So apparently they're not the same. It makes it very clear with that previous example, just by looking at the number of votes that a player owns can actually be very deceptive. All right, so a couple more things to talk about for this section before we move on to our next part of Chapter 2, which will be bonds off power. So first off, let's talk about what are called dictators. So consider your voting system where you've got 11 as the quota, and then you've got your weights as weight 1 is 12, weight 2 is 5, and weight 3 is 4. Here, one of the players, P1, actually has enough votes to carry a motion single-handedly. In this situation, P1 is in complete control. If P1's for the motion, it passes. If they're against it, then it fails. So clearly, in terms of power, P has all the power. And if that happens, then we're going to call P a dictator. In general, a player is a dictator if that player's weight is bigger than or equal to the quota. Since the player with the highest weight was P1, we can conclude that if there's a dictator, then it has to be P1. So that'll always be the case. When P1 is a dictator, all the other players, regardless of their weights, have absolutely no say on the outcome of the vote. There's never a time when their votes really count. A player who never has a say in the outcome of a voting is a player that has no power, and so kind of a fun way to describe them, we're going to call them dummies. All right, so some unsuspecting dummies. Let's kind of give you an example of this. So you've got 4 college friends. P1, 2, 3, and 4 decide to go into business together. 3 of the 4, P1, P2, and P3, invest $10,000 each, and each get 10 shares in the partnership. P4 is a little short on cash, only invests $9,000, gets 9 shares. As usual, 1 share equals 1 vote. The quota is set at 75%, which here means that Q would be 30 out of the total of 39 possible votes. Mathematically, stripped of all the irrelevant details of the story, this partnership is just the weighted voting system of 30, 10, 10, 10, and 9. So if you think about it, and we'll talk more about it on the next slide, the only way to get 30 is for these 3 to agree. 9 has no say in it at all. It's going to be a dummy. So everything seems to be fine with the partnership until one day P4 wakes up to the realization that with the quota set at 30, he is completely out of the decision-making loop, like we had just mentioned. For a motion to pass, P1, 2, and 3 all have to say yes. And at that point, it makes no difference how P4 votes. Thus, there's never going to be a time where P4's votes are going to matter with the final outcome of a vote. Surprisingly, P4, with almost as many votes as the other partners, is just a dummy in disguise. Okay, another example here. I think this will be one of the last ones we look at before we're done with this section. So consider the voting system of 12, 9, 5, 4, and 2. Here, P1 is going to play the role of what we'll call a spoiler. While not having enough votes to be a dictator, the player has enough votes to prevent a motion from passing. This is because if you look at the other player's votes, 5 plus 4 plus 2 is 11. That's less than the quota of 12. That means that even if all the other players were for it, without P1, the motion's never going to pass. If that happens, we are going to say that P1 has veto power. So they're not a dictator because they don't have enough for it to pass on their own. And the other ones aren't dummies. They still have a say in what's going on. But we're going to say that P1 has the veto power, meaning if they're not for something, then it can't pass with the help of the other 3. So a player who's not a dictator then is going to have veto power if a motion cannot pass unless the players votes in favor of the motion. In other words, a player with veto power cannot force a motion to pass, but they can force a motion to fail. If we let W denote the weight of a player with veto power, then the 2 conditions can be expressed mathematically with the following inequalities. Is that W is less than Q, implies that the player is not a dictator, and V minus W less than Q implies that the remaining votes in the system are not enough to pass a motion. All right, so veto power, here it is summed up one more time. A player with a weight W has veto power if and only if that W is less than Q, so it's less than the quota, so they're not a dictator, and that the number of votes minus W is less than Q, where the number of votes is equal to W1 plus W2 all the way up to WN. All right, guys, that is it for 2.1. That is it for our introduction to the mathematics behind power and behind weighted voting. We'll be talking in 2.2 about Banzai power. I will see you guys then.